Okay, so we're going to look at some example problems for creating confidence intervals for large population proportions. So we look at an article that's called "How Well Are U.S. Colleges Run," and describes a study of 1,031 adult Americans. The survey was carried out by the National Center for Public Policy, and the sample was selected in a way that makes it reasonable to regard as the sample representative of adult Americans. Um, of those surveyed, 567 indicated that they believed a college education is essential for success. So we want to see, what is how confident can we be about the true proportion of Americans? Where can we say that that's likely going to be? So we start off by making a point estimate. So we say, okay, well, p hat. We need to say, so in our study, we said 567 Americans out of 1,031. And so that equals, let's see, 567 out of 1031. And that gives us basically 55%. So we're going to go with 55%. So that's our point estimate. Now we've got to cover three things real quick. Okay. First off, do we have, is n times p greater than or equal to 10, and is n times 1 minus p greater than or equal to 10? Well, so this is going to cover whether or not we can consider this normal or not. Well, n times p, this is going to be 1031 times 0.55, which that is certainly greater than 10. That's almost 500. And likewise, we're going to end up with 1031 times 0.45. Is that greater than or equal to 10? That's also good. So we can go ahead and say yes. Because we've checked this, that is normal. It's reasonable to assume normality now. So we can go ahead and say that's good. 2, is the sample less than 10%? So is n less than 10% of the population? Well, we have 1,031 adult Americans. That's a small, that may seem like a lot of people, but think about how many adult Americans there are. There's way more than, 10,000 adult Americans. So we're very good here. So that's satisfied. And 3, is it random? Is it reasonable? And we can go ahead and say yes. That they had a big part in this article. The survey is carried out in a way that makes it reasonable to regard as a sample representative. So it go ahead and covers that for us. So we can go ahead now that we've checked all this, to go ahead and use a confidence interval. So I'm going to move to the next page. So let's say we want a 95% confidence interval. Oops, I know spell. Confidence interval. And we have our p hat, we had as 0.55, and we had our n as 1,031. So we're going to go ahead and create this. Now, basically, based off of these numbers, we have a mean and a standard deviation, right? So our standard deviation here for our p hat is going to be the square root of 0.55 times 0.45, which is, that is the complement of 0.55. And then we divide that by 1031. And so that number equals, so we got the square root of 0.55 times 0.45 divided by 1031 gives us 0.0155. So we got 0.0155. So we could go ahead and create this using the formula that we had before. So we had p hat, which is 0.55. We're going to go forward 1.96 times 0.0155, and we're going to go backwards, so subtract away 1.96 times 0.0155. And you could figure out these numbers. Now, your calculator will also do this for you. Thank goodness. And you only need the top two numbers. You only need these. Well, really, excuse me, the top three numbers. You need this information right here. So I'll show you how this is done. So you go to your calculator. You're going to go to you're going to go to stat. Sorry. You're going to go to tests. And you're going to go down to where it says 1 prop z int. Excuse me. 1 prop z int. So that would be letter A. So if we go to 1 prop z int, it's going to bring up some options for us. So x is the number of successes. So we don't even have to figure out the actual p hat value. The number of successes we had was, let's see, 567. So we do 567, and our n was 1031, and our confidence level is at 95%. And we're going to go ahead and calculate. Well, it's going to say, okay, well, 0.51958, so 0.52 to 0.58. So we got 0.52 to 0.58. So this, and if you type these in, this would end up giving you basically the exact same information. So your confidence interval, the way that you would write that is going to be, I'm going to do this in the blue up at the top. So your confidence interval is going to be 0.52 to 0.58. So based off of our sample and sample size, we could say with 95% confidence that the real proportion of Americans who think that higher education is important would be somewhere between 52% and 58%. Because if we took a same sample of 1,031 American adults, then we would end up getting information about like that. We could estimate that that's probably where that occurs. Okay, so that's what this number means. Okay, so let's look at this one more time. So article, we said 9 out of 10 drivers admit in a survey to having done something dangerous. So reported the results of 1,100 drivers. Of those surveyed, 999 admitted to careless or aggressive driving during the previous 6 months. Assuming that it is unreasonable to regard this sample of 1,100 as representative of the population of drivers, we can use this information to construct an estimate of P, the proportion of all drivers who have engaged in careless or aggressive driving in the past 6 months. So we need to start off, so I'm going to cut to the chase here. So we're going to start off with P hat. So P hat is going to be 990 out of 1,100 drivers. Okay, so we have this information. Now, let's say we want to create a 95% confidence interval for this. Okay, so what we need to do is we go back. So this is like our successes. And this is our sample size. Without doing a lot of the math, we can use our calculator to help get this. So we go back and we're going to run, we're going to go to stat. We're going to go to calculate. We're going to go down to, we're going to go to tests, and we're going to go to 1 prop z int, and we are going to use our new information. So 990 out of 1,100 at 95%, calculate, gives us between 88% and 92%. So between 0.88 and 0.92. Between this percentage, we see that this is where we could expect samples of a same size to lie based on what we have. Because since this is such a large sample, the standard deviation is going to be very small. And with that small standard deviation, we can be very, very confident that this number exists. Now, what happens, let's say, if we want to know a particular size? Okay. Now, here's the way that we go about this. So researchers have found biochemical markers of cancer in the exhaled breath of cancer patients, but we haven't proven the effect of clinical diagnosis yet. Okay, so they're going through this study and they're trying to estimate the long run proportion. So they're gonna ask at the very bottom, how many different breath specimens? So how many people will we need if we want to estimate the long run proportion of correct identifications for this dog to within 0.05 with a 95% confidence interval. So we're trying to get it within 0.05. So in a sense, we're going to have our p hat, and we want no more than 0.05 up and 0.05 back to contain 95%. So that's what we're looking for. We know now the range that we want, but we want to know how many people should we sample in order to be this sure, in order to be within 0.05 and being 95% sure at the same time. So we go to a trusty formula for ourselves. So our trusty formula here is going to be N equals, okay, it's going to be P times 1 minus P times our z-score over our standard deviation, okay, squared. Or excuse me, not standard deviation, our bound. So our bound is that difference left to right. So it's like we have p hat, and we go forward b and back b. So for this, we're going to say N equals, so P, nowhere in the article does it mention what that's going to be. So we conservatively say 0.5. We do 1 minus 0.5, and we need our z-score. So associated with 95%, do you remember which z-score that is? It is 1.96 divided by our bound, which is going to be 0.05, and we square that. Now, the smaller this number is, the larger this number is going to be. The smaller that our bound area is, because we're dividing by it and then even squaring it, the much larger n is going to be. So if you want to be accurate, you're going to need a very large sample size in order to do that. So this is one thing that we cannot actually just use our calculator for. It's not going to give us. So we have to go ahead and actually calculate this by hand. So we do 0.5 times 0.5, because that's 1 minus 0.5, and then we're going to bracket, so we get 1.96 divided by 0.05, close the bracket, square that, boom. So we're going to need a sample size north of 384.16. So we're going to say our sample size is going to be 385 people. So if we got that many people, then our 95% confidence interval would be within 0.05 on either side. So 5% left or right of our mean. And that's going to be guaranteed by this formula.